So we talked the other day about circular motion and how we work out angular velocity and how that relates to linear velocity. We're now going to look at the acceleration that's associated, but we're just going to restrict ourselves to uniform circular motion. So in other words, angular velocity will be constant. So you might be thinking, well, hang on, if angular velocity is constant, surely the acceleration is zero. And that would be true. The angular acceleration is zero, but there will be acceleration linearly. So that's basically what we're looking at. How's the acceleration work in this circular motion? So now the magnitude of the linear velocity must be constant. Because if I just said the angular velocity is constant, and remember linear velocity is equal to the radius times angular velocity, so it must also be constant as well. Well, it's the size that's constant. It will be going off in different directions depending on which point in the circle that we're looking at. So it actually does create a change in velocity. So here's our circle we're going around. There's the point A. And A is going to move to P with a constant angular velocity. But the acceleration will be the change in that velocity. Now, whilst the magnitude's the same, the direction will be different. Because at A, remember we said we go in the direction of a tangent. So A, we're going off in this direction at 90 degrees to OA. But P would be going at 90 degrees to OP. Now, if I was to join those vectors up, so the initial direction is V. The change, therefore, must be the gap between those two vectors. So the red line, because we finished off going off in this direction, well, that would be equivalent to going down to V and then across so on. Now that angle there, we could play around with the geometry because we know these are all 90 degrees and so on. So we could easily show that that angle there turns out to be theta. But that triangle will be similar, therefore, to triangle OAP. Because the angles theta, remember the size of V and V dash we said were equal. Well, in our triangle OAP, they're both radii. So they're both isosceles triangles with the angle theta being at the top. Okay. So I can play around with the ratio of sides in similar triangles. So change in V, whatever the length of that red vector is, over AP would be the same as V over R. Rewriting that, so the change in velocity, acceleration, will be V times AP over R. But acceleration, is change in V over change in time. So there's an expression for acceleration. VAP over R times delta T. Now, I'm interested in looking at what happens as the change in time is close to zero, because that will give us an instantaneous change. So at that point, as angle T approaches zero, it's actually travelling on the arc AP rather than the chord AP. But as time approaches zero, the length of that arc and the length of that chord will be getting close to being the same thing. It's only as time goes on that that arc gets bigger than the chord. So if we're talking about close to zero, that length must be the same. So I now can say, well, the acceleration, therefore, would be the limit as the change in time approaches zero, V times the length of the arc AP over R delta T. But we also know distance equals speed times time, or speed equals distance over time. So arc AP is equal to V times delta T. So subbing that in. Now the delta T's end up cancelling, and I end up with V squared on R. There is now no delta T in there. So that limit is exactly V squared on R. Don't panic. If you were asked to prove this, I would not recommend going this way. I just want to show you we can build it up through the vectors to show that, hey, yeah, this is the way. So we just need to know that the acceleration in uniform circular motion has the size V squared on R. its direction, the direction of this red vector, is towards the centre of the circle. It'll always be towards the centre of the circle. So what do we need to know? We know acceleration is v squared on r. If we're talking about angular velocity, then it would be r omega squared, because remember v is equal to r times omega. Forces is what we start with in these questions. So force is just mass times acceleration. You might even recognise this formula. Force is mv squared on r. Or if it's an angular velocity, mr omega squared. That's what we call centripetal force. So let's have a look at a question. 2003 paper. Particle P of mass m moves constant angular velocity, circle radius r, its position at time, so you'll notice it's using the parametrics for the circle. R cos theta, R sin theta. Theta is omega t. Show that there is an inward radial force of magnitude mr omega squared. So in other words, it's asking us to prove that force is mr omega squared. And as I say, I don't recommend that we do it the way I just did it. There is a much, much easier way now that if we do it with our parametrics. So there is our circle. Say, broken it up into the parametrics. The x direction is r cos theta, the y direction is r sin theta. So if I look at the x displacement, well, and the y displacement, differentiate once to get the velocity displacements, the velocity equations. I get minus r sin theta, but I'm differentiating implicitly because, remember, velocity is with respect to time. So because I've differentiated with respect to theta, I go to multiply by d theta dt. But d theta dt is angular velocity. So I can sub in omega for the d theta dt. So I get that the horizontal velocity is minus r omega sine theta. I can do a similar thing with the y one and we end up with r omega cosine theta. Let's find the acceleration. Differentiate again. It's constant angular velocity here. So I don't have to worry about the omega. I know that's a constant. The only thing I'm differentiating is the sine theta, and so I get cosine theta. But again, that's differentiating with respect to theta, so I've got to multiply by d theta dt. But d theta dt is omega, so I get minus r omega squared cos theta. But hang on, x is r cos theta. So acceleration is minus omega squared x. That hopefully looks very familiar. It's simple harmonic motion. Circular motion really is just simple harmonic motion. Because if you are just looking at its motion horizontally, it will be going backwards and forwards in simple harmonic motion. But have a look what happens in the y direction. Same thing. It's also simple harmonic motion. In fact, it does not matter which direction we look at the circle. If we just look at the circle flat, so all we see is it moving backwards and forwards, it'll always be in simple harmonic motion. Still, we wanted to prove that that force is equal to mr omega squared. So we now have the two components of acceleration. So I can join the vectors or the components together. The size will be the hypotenuse. That'll be our acceleration. So it'll be the horizontal component squared plus the vertical component squared. Sub that in, and I get omega to the power of 4 x squared plus omega to the power of 4 y squared. But of course, x squared plus y squared is r squared. That's the equation of a circle. And so we get that the acceleration squared is omega to the power of 4 r squared. Acceleration is r omega squared. Now we need direction towards the center. Oh, sorry. Force is equal to mass times acceleration. So we have our force equals mr. That's how I would suggest you go and prove force is equal. That's much easier, I think. The only thing we have to consider now is the direction. The direction will be this angle alpha in our triangle. Okay, going back to our triangle. Well, so it's going to be the inverse tan of the vertical component over the horizontal component. Well, the vertical component was minus omega squared y. So inverse tan of y on x. Well, hang on. Go back to our original diagram. That's theta. So it is directed towards the center. That angle does turn out to be theta. We're going with a telecommunication satellite of mass m, orbiting the Earth, constant angular velocity, distance r, from the centre of the Earth. Gravitational force exerted by the Earth is am on r squared. A is also a constant. Considering all other forces on the satellite to be negligible, we're going to show that the radius is the cube root on A on omega squared. There's Bob. The resultant force in circular motion is centripetal force. Okay? So all the forces, so mx double dot, when we're talking about circular motion, is mr omega squared or mv squared on r, depending on whether you're talking about angular velocity or linear velocity. So there's where I've defined at some point, my resultant force, which will be going towards the centre of the circle. As long as we're all in agreement that it's always going towards the centre of the circle, we're going to be fine. Right? So the direction of that is towards the centre of the circle. Okay. What else do we have? We have the force due to gravity, which also happens to go towards the centre of the circle. No matter where it is, it'll always be going towards the centre of the circle. Am on r squared. Therefore, the resultant force, mr omega squared, is equal to am on r squared. What looked like a really tricky question, now, when you look at it, actually is rather simple. I just have to make r the subject. R cubed is a on omega squared, so r is the cube root of a on omega squared. That's all that's really saying. A string. We have a string. Imaginary string. Ooh. There we go. Okay. 50 centimetres long. It'll break if I put a mass exceeding 40 kilograms. So here's my piece of string hanging there. Put a weight on a 40 kilogram. Oh, jeez. Broke the string. But a mass of 2 kilograms is put on it. Oh, you beauty. It'll hang on there. But I'm going to revolve it in a circle. Hey. What's the greatest angular velocity that I can spin my little bob, which may be imparted as a technical word, without breaking the string? So the first piece of information tells us how much force, although when we're talking about a string, that force is called tension. You might have heard the term tension in the string. It's all it's talking about. How much force can our string handle here? So all right, here it is. I'm just there doing nothing with it. Just holding it there. There's Bob at the end. Whew. What forces are acting on my string? Gravity. Thank you. So we'll have our resultant force. I'm going to say my resultant force is going down in this case, and it is gravity. And I'm not doing anything else than just hanging there. So we know there's going to be tension in the string. Whenever you have something attached to a string, there will be a tension force going up the string. Okay? So that is the other force in this problem. T for tension, we shall call it. But what do I know? The resultant force, because it's hanging there at the moment, and it's beautifully stable. So the resultant force is mg minus the tension. But in this case, it's 0. Because it's not moving. It's just hanging there. Nothing's happening. So mx double dot is equal to 0 at this stage. And so therefore, my tension, I can work out how much tension's in the string. It will be mg, rearrange it so I get 40 times 9.8. The units for tension, or any force for that matter, is newtons. So I know this string can handle 392 newtons. But now I'm going to spin it. So now it's horizontal. So there it is. I've captured it at some point in its circle. The resultant force will be going where? Towards the centre, because we are now in circular motion. So my resultant force is going inwards. What other forces are on this horizontally? We're just looking at horizontal forces only. Okay, no, fair enough. Horizontal gravity, which is equal to 0, because there is no such thing. So therefore, horizontal gravity. But you are right. You are right. Horizontal gravity is there. But there will still be tension, because the string, it's still attached to the string. So now, tension is equal to the resultant force in centripetal force, mr omega squared. But we know how much tension this string can handle. It's 392 newtons. So let's sub it in. The radius, of course, is the length of our string. Where is it? 50 centimetres long. So omega squared, it can handle us rotating at 2 root 98 radians per second. before the string will break. Okay. Again, this is just a starter on our idea of circular motion. Cambridge 9A. I know some of you tried to do Cambridge 9A before.